Section 7.4, transforms of derivatives, integrals, and periodic functions. We're going to just do derivatives and integrals. So the question is how to start with this one, how to find the Laplace for a derivative, say the first derivative with respect to t, or maybe for the second derivative. And at some point, can you find a pattern or not for this? Well, let's see how to do this. We can use the definition. So dy dt can be written as f prime of t. The definition of Laplace 0 to infinity e negative st times usually f of t here, but we're doing Laplace for f prime of t dt. Then we can use integration by parts, which I'm not going to go in depth, like step by step in details for this. But using integration by parts, it gives us negative est f of t. Of course, I'm going to just use 0 to infinity. Usually should be limit, but you know what this means. S, the integral 0 to infinity e negative st f of t dt. And if you do this again, evaluate the infinity. So e to the negative infinity is 0. So this is going to go to 0 as t approaches infinity. And so it's infinity minus e to the 0, 1 f of 0. And the last one is s. This is the Laplace of f of t. So that gives us a formula to find the Laplace of the derivative of f. So we can rewrite it as the Laplace of the derivative is s capital F of s minus small f of 0. That's the formula to find the Laplace for the first derivative. Similarly, we can run through the same way and do integration by parts to find a formula for the Laplace of the second derivative of f, which is going to turn out to be negative f prime of 0 minus s Laplace of f prime. That's from the first derivative. And then this will be s f of s minus f of 0 minus f prime of 0. So this goes here. Or it can be rewritten as s square f of s minus s f of 0 minus f prime of 0. Notice the difference between small f and capital F. So that's the Laplace for the second derivative of t formula. You can do it for third derivative, fourth derivative. Now, as a theorem, so for the nth derivative of f, the way we do it, we introduce a theorem. It's called transform of a derivative. And what does it say? Under specific conditions that f of t, f prime of t, f double prime of t, all the way up to f n minus 1 of t, all these derivatives are continuous. If these are continuous over the interval 0 to infinity and are all of exponential order. And if f double prime of t is piecewise continuous, so the nth derivative, we are working with the nth derivative, not second derivative. And if the nth derivative is a piecewise continuous on the same interval 0 to infinity, then the formula to find the Laplace for the nth derivative of f of t is given by Sn f of s minus Sn minus 1 f of 0 minus Sn minus 2 f prime of 0 minus minus the nth minus 1 derivative at 0. Keep in mind, capital F of s is the Laplace for small f of t. So this is the formula for the nth derivative. So the first two that I showed, those are special cases of this one, the first and the second derivatives. Now we're going to put this together with another thing they're going to introduce now called convolution and come up with stuff. So I'm building on tools to help us for the next section. So for the convolution, for two functions, if we have two functions f and g are piecewise continuous over the interval 0 to infinity, then the convolution of f and g is defined as f. This is asterisk, but I'm gonna just say star f star g is the integral from 0 to t f of tau, the Greek letter tau, times g of t minus tau d tau. That's the definition of the convolution of two functions. And convolution functions, or convolution is it commutes. So commutes means f convolution with g is the same as g convolution with f. To apply this as an example, find the convolution of the two functions f of t equals e negative t and g of t equals cosine t. So all we have to do is apply the definition. E negative t convoluted with cosine t is the integral 0 to t e negative, that's a e negative lambda, negative tau becomes positive tau, times cosine t minus tau d tau. And now how do we integrate this? Well, integration by parts is required. From the integration by parts, we have this trick, LIATE, for exponential and trig. So trig comes first before exponential, so that's going to be my u. U is cosine t minus lambda, not lambda, tau. So du, differentiating here with respect to that, cosine, derivative of cosine is negative sign, but there's a negative here, so that becomes sine t minus tau d tau. That's du, and the rest is dv. dv is e tau d tau, so v is e tau. So let's see what we get. We get uv e tau cosine t minus tau, uv minus the integral v du sine of t minus tau d tau. Of course 0 to t, and here 0 to t. Now we need to evaluate this. We do integration by parts again, so I'm going to do it on the side here. T minus tau d tau. So if u equals sine t minus tau, du is negative cosine t minus tau d tau. And dv is e tau d tau, so v is e tau. So then uv, so that would be e tau sine t minus tau, uv minus the integral of v du, e tau, and du is negative, become positive, t minus tau d tau. So now we can substitute that in. E tau cosine t minus tau, and then we have a minus all of this, e tau sine t minus tau minus the integral e tau cosine t minus tau d tau, 0 to t. All this 0 to t, 0 to t. So now notice we're not going to do it again. This is the same as the original one. So if you add it to both sides, you get 2 copies of that. And then divide by 2, then that gives us 0 to tau e tau cosine t minus tau d tau equals 1/2. We get et minus cosine t plus et sine t e tau with the hope there's everything looks good. So now that's how we found the convolution for the 2 functions. Now we introduce a theorem. It's called convolution theorem. It says if we have f of t, g of t, piecewise continuous functions, over the interval 0 to infinity and of exponential order, then we have the Laplace of f convoluted with g is the Laplace of f of t times the Laplace of g of t. Or you can write it as capital F of s times capital G of s. As an example, evaluate the Laplace of the integral 0 to t e tau cosine t minus tau d tau. So here we have 2 functions, e tau and the cosine t minus tau. So by the theorem, f of t here again is e to the t, and g of t would be cosine t. So the Laplace of f of t times the Laplace of cosine t. This is simple, 1 over s minus 1, and this is s over s squared plus 1. And if you multiply top by top and the denominator by the denominator, you get this one. So that's how the theorem helps. Now, as a note, we can get also the inverse form of the convolution theorem. What does it say? We need to look at the inverse of that. Now, the convolution theorem is sometimes useful, of course, of finding the inverse of Laplace of the product of 2 functions, of two Laplace transforms. So to get the Laplace of f of s times g of s, it's kind of going backwards. It's basically f convoluted with g. And to apply this, we can look at an example. Evaluate the inverse of 1 over s minus 2 times s plus 3. So here we have 2 functions. Capital F of s, I'm going to call it as s minus 2, and capital G of s, 1 over s plus 3. So what we do here, if we find the inverse Laplace of f of s, which is f of t, in this case supposed to be e to the negative positive 2t, and the inverse Laplace of g of s is g of t, which is e negative 3t. So then we know that the Laplace of what we are looking for is f convoluted with g, and by the definition of convolution, 0 to t, f of tau times g of t minus tau d tau. d tau. So when we substitute the functions in 0 to t, e2 tau times g of negative, not g, e negative t minus tau d tau. And that would give us 0 to t, e negative 3t, and 3 tau with 2 tau, 5 tau. So e to the 5 tau d tau. And you can take e negative 3t out because that's considered as a constant. The variable is tau. So e negative 3t times 1 over 5 e 5 tau, the integration, 0 to t. And if we substitute that in, we get e negative 3t times 1 over 5 e 5t minus e, so this is tau, e negative 3t times 1/5, e to the 0 is 1. You can factor, if you like, e negative 3t over 5 out. That will leave e to the 5t minus 1. We can look at another example. Inverse Laplace of 1 over s plus 1 square. So how do we do this? So to find the inverse Laplace of this using convolution, we can look at this as two functions. One of them 1 over s plus 1, the other one 1 over s plus 1. So in this case, f of s is 1 over s plus 1, and g of s is also 1 over s plus 1. That's fine for two functions to be the same, it's okay. So the inverse Laplace of f of s is going to be the same as the inverse Laplace of g of s, which is e negative t. Then the inverse Laplace of 1 over s plus 1 square is f convoluted with g. And that gives us 0 to tau, f of tau, g of t minus tau, d tau. So what we get here, the integral from 0 to t, e negative tau times e negative t minus tau. Notice how it's easy to confuse between tau and t. So now what do we get after that? When we multiply this out, we get e, there's a tau and negative tau, that's a 0, d tau, and e negative t that can be outside. So now e negative t times tau from 0 to t. Substitute that in, you get t e negative t minus 0. So we could use, as you noticed, convolutions as a tool to help us find the inverse Laplace of a given two given functions. So we use derivatives and integrals here to see and introduce the convolution theorem and the definition of convolution.